Welcome back. In this video, we will solve problem 6.94 and 6.95. So let's start with 6.94. The statement is the beam has rectangular cross section as shown. Determine the largest load P that can be supported on overhanging and so that bending stress does not exceed 10 megapascal. So you can see this is the overhanging beam where there is a concentrated load P at both ends. These are the supports and allowable bending stress is 10 megapascal there. So you have to find this load P, and the cross section of this beam is rectangular having width 150 millimeter and height 250 millimeter. So let's start with the solution. So if you first thing is that if you remove this support, so definitely there will be a reaction forces at this point. So let this is R1, let this for reaction forces, this is your point 1 and this is your point 2, and when you remove the support 2 you will have a reaction force R2. Now this R1 and R2 can be found by using equilibrium condition. So first equilibrium condition is that sum of all movement about point 1 is equal to 0 and taking the counterclockwise movement as positive. So about point 1, the first movement is this P into perpendicular distance is 1.5, and that is this will produce a counterclockwise, so it will be positive. The second movement is due to R2 and perpendicular distance is 1.5 and it is producing counterclockwise, so it will be also positive. The third movement is due to this P and this perpendicular distance is 3 meter and this will be clockwise, so it will be negative. Their sum must be equal to 0. So I will write P into perpendicular distance 1.5 and that is positive, plus R2 into perpendicular distance 1.5 and that will be also positive, minus P into perpendicular distance is 1.5 plus 1.5 which is 3. So P into 3, their sum must be equal to 0. So again you will have 1.5 P plus 1.5 R2 minus 3P is equal to 0. So from here 1.5 R2 minus 1.5 P will be equal to 0. So it means that R2 is equal to P. Now you have this P, you can find R1 by using another equilibrium condition that sum of all forces along y direction must be equal to 0. So four forces minus P plus R1 plus R2 minus P will be equal to 0. So I will write minus P plus R1 plus R2 which is again P minus P is equal to 0. So this will cancel with this, so R1 will be equal to P. Now you have both R1 and R2. You can just use them to draw the shear force and bending moment diagram, because we will need maximum bending moment, absolute maximum bending moment. So we will get it from bending moment diagram. So we will draw the bending moment diagram. We will need shear force moment diagram as well. So what we will do is that we will take the vertical line from the end of this beam and there is a horizontal line to draw the shear length. X will be in meter and you will have shear force. Now let each division is P. So this is P, this is minus P. So you can see that at this point you have minus P, that is downward. So first point will be this one. Now moving from P to R1, there is no other load, so this will remain minus P till this point. Okay, at this point you have a load of R1 which is equal to P, so minus P plus P will bring it to 0. So the shear force will change from minus P to 0. This will be a straight line. Okay, now from R1 till R2 there is no other force, so this will remain same, and we will have now at R2 we have a load of R2 which is plus P, so it will move to this point. So I will draw, this will be P. And moving from R2 till end, we have no other, so it will remain same. But at point this, we have minus P, so plus P minus P will bring it to 0. So it will be your shear force diagram. Now what about bending moment diagram? So again, we have to draw horizontal line that will show X in meter, and we have bending moment. The first area under the shear force diagram will give you bending moment, and this is square, so it will be minus P into 1.5 because this length is 1.5. So it will be minus 1.5 P. So let this division is 0.5. This is 1.5, 1 P. This is minus 1.5 P. So at this point you will have minus 1.5. So again you can see this shear force is a horizontal line, so bending moment will be 1 degree higher and slope will be decreasing. So we will get the bending moment like this. Again, moving from here, there is no other bending moment, so it will remain same horizontal. So this will be your horizontal. Now this is minus 1.5 P. Again, this area is 1.5 P. So minus P 1.5 P plus 1.5 P will equal to 0. So it will be 0 and we will get the bending moment like this. Okay. Now from this bending moment diagram, you can see that maximum absolute value of bending moment is equal to minus 1.5 P, which is equal to 1.5 P. Clear? And we know that maximum stress is equal to maximum bending moment into C divided by I. So we have this, we do not have C, we do not have I. So since this cross section is rectangular, the width is 250 millimeter and height is width is 150 millimeter and height is 250 millimeter. So its neutral axis will pass through the half of this. So this is your neutral axis, and C will be this one, which is equal to 250 divided by, I will write C is equal to 250 divided by 2, which is equal to 125 millimeter. So C is equal to 125 and in meter it will be 0.125 meter. And what about I? So I will write I is equal to, for rectangular cross section, it will be equal to 1 over 12 B into H cube. So you have I is equal to, I will draw a line so that you should not confuse, 1 over 12. Breadth is 150 millimeters, so in meter it will be 0.150 and height is 250 millimeter. So 0.25 whole cube. So when you solve this, you will get I is equal to 1.9531 into 10 raised to power minus 4 meter power 4. Now you have maximum bending moment, you have C, you have I, you can just put it in this formula. Clear? So you will get the required P. So maximum bending stress, I will write it, is equal to maximum bending moment into C divided by I. So maximum bending stress is given as 10 megapascal. So you can just put the value 10 into 10 raised to power 6 is equal to, this maximum is 1.5 times P. C is given as 0.125 divided by I is 1.9531 into 10 raised to power minus 4. So you can just put, you need this P, so P will be equal to 1.9531 into 10 raised to power minus 4 multiplied by 10 into 10 raised to power 6 divided by 1.5 multiplied by 0.125. So when you solve this, you will get the maximum concentrated load P comes out to be 10.4 kilonewton. So this is the answer of our problem 6.94. Now we'll move toward the second part of the problem. The second part of the problem is given as I have copied it below. So you can see that in second part it is given that the beam has a rectangular cross section. If P is equal to 12 kilonewton, determine the absolute bending stress in the beam and sketch the stress distribution over the cross section. Rest all the things are same. So if you are new to this problem 6.95, so you have to draw the shear force and bending moment diagram to get the maximum bending moment, which is already described in problem 6.94. So we will just use this formula. We have been asked to find the maximum bending stress, that is equal to maximum moment into C divided by I. So maximum moment that we have taken from, we will take it from here. You can see that is 1.5 P absolute. So 1.5 P, P is given as 1.5 P is given as 12 kilonewton. So 12 into 10 raised to power 3. So you will get the maximum moment will be 18,000 Newton into meter. Now C is also explained in here. So you can just see 0.125 for this rectangular cross section and I is this. So if you are new, then I will recommend to first go through problem 6.94 and then come back to 6.95. So I will write the value C is equal to 0.125 and I that we have calculated was 1.953 into 10 raised to power minus 4 meter power 4. Now you have all the values. You can just put sigma max, our maximum bending moment is equal to 18,000 multiplied by 0.125. This is in meter divided by I, which is 1.953 into 10 raised to power minus 4. So when you solve this, you will get maximum bending moment comes out to be 11.5 megapascal. So this is the answer. Now we have been asked uh, to to show it or to sketch the variation. So for that I will draw the cross section of this beam, rectangular cross section. So let this is the width and this is the height. Okay. So the neutral axis will be the at half of this. So this is its neutral axis. Now you can see that due to this load, the beam will bend like it will bend like this, because the upward force will be there, R1 and R2. So the upward layer will be in tension, this will be in tension, and the lower portion will be, if I draw it like this, so this will be in compression. Okay, and for that you know that maximum stress is at this point. Okay, I will draw a vertical line, horizontal line. So this will be the maximum stress, and the bending stress is 0 at neutral axis, so it will be like this. And same is the case, you have to I will draw it again. Okay, so at above we have tension, so it will be just like, if I draw line like this, so the upper one will be in tension, the stress will be like this, and lower one will be in compression. Same, you can draw it over here. All this will be in compression, and similarly here this will be straight lines. Okay, so this is the variation stress distribution. I will write stress distribution. I hope you have liked both this problem and you have also learned them. Again, if you have any question, you can ask me in comment section. Those who are new to my channel, then subscribe it and press the bell icon so that you can get notification about my latest video. Do comment on the videos so that I may know about the feedback. Thank you.